Science Council and basically leading the effort in the multi-messenger view of Sagittarius star and M87, which is exactly what she will present to us today. Thank you.
Thank you, Martha. Now, no feedback. Good morning, everyone. Thank you for having me. And thank you, Martha and Pierre, for the welcome. It's very nice to be with you all today. I tend to speak very fast when I get excited. And I think this science is really cool. So if I speak too fast, somebody just raise their hand and be like, I will slow down. So it's really fun to be here to talk about the Event Horizon Telescope. I, in particular, with this collaboration, am a member of the Multi-wavelength Science Working Group. So what that means is that I help coordinate a whole bunch of different observatories that take observations together with the Event Horizon Telescope. So today I'm going to talk about two supermassive black holes, Sagittarius A star here in the Milky Way galaxy, and M87 star, which is the black hole in the biggest, brightest galaxy at the center of the Virgo cluster of galaxies, which is a cluster of galaxies that's fairly close to the Milky Way, but it's not here in our own Milky Way like Sag A star. So it's really a pleasure for me to be here with all of you. I've been on sabbatical on a visit to Grenoble, to the EPAG CNRS there for the last 8 months. And so it's really nice to come up and meet more CNRS colleagues and students here. Okay, diving in. Let's see if this is going to play. Oh, it worked so great when we tested it out. Now it's not working. That's okay. I will do without. Okay. Oh, maybe it's just not. There we go. No. Okay. All right. So I'm going to do the classic thing of giving you the most important information right at the beginning. So the number one thing that you need to know is that for Sagittarius A star, this beautiful supermassive black hole that we see here in the kind of orange image up at the top, this is an image of the emission from very close to the event horizon of the black hole. And the Event Horizon Telescope, which is, abbreviated EHT throughout my talk, offers really some of the highest resolution images that humans have ever taken. The resolution here is, below the fineness, the resolution of a human hair. It's very, very, very tiny on the sky, this incredible black hole. And so the instrumentation and the technology and the people and the intelligence to collect this image is really quite spectacular. We confirm that the supermassive black hole in the Milky Way galaxy has a mass of 4 million times the mass of our sun. We've known this for a long time from measurements of the orbits of stars around the supermassive black hole. I won't talk about this too much, but this is really impressive work for which 2 teams won the Nobel Prize in 2020. So these are the groups led by Reinhard Genzel and Andrea Getz. And so these dynamical studies where we watch Keplerian orbits, stars orbiting around the black hole, are some of the most sensitive mass measurements that we can make of a supermassive black hole. And when we take then that information combined with the images of the photons very close to the black hole, we find a nice consistent picture where we think we can measure the mass of this black hole with very good precision. And astronomy, as many of you I hope know, is not a science of great precision when it comes to things like distances and masses, especially not on cosmological scales. So this is one of our best measurements of a black hole mass for a supermassive black hole. The other black hole I'll talk about today is M87 star, and I'll come and talk more about M87 in the second half of the talk. But combining these 2 images we've taken of Sagittarius A star and M87 star, the star, for people that aren't familiar with this, just means it's the black hole at the center of the galaxy. In the case of M87, the galaxy itself is also called M87. So we use the star just to specify that we're talking about the black hole. And so these 2 images together, when we take them as 2 measurements that can be made of this horizon scale emission, confirms general relativity over 3 orders of magnitude in mass. So we don't have reasons yet to mistrust general relativity, but we love to break theories. And so we're always trying to find a way to push on the theory and see if we can find a chink in its armor, find a way in which it's wrong so we can learn a little bit more. So far, we haven't managed to find find any discrepancies with GR with these EHT images, and instead we just confirm that it's valid over these very large differences in mass. And then multi-wavelength, so again, I'll use an abbreviation here, using MWL for multi-wavelength. The multi-wavelength data, I can turn this off so it doesn't, or maybe I'll just hand it to you, Pierre, so I don't get feedback. Thank you. Just a little further away, I think. The multi-wavelength observations allow us to look at the total environment, so what's happening around the black hole at larger scales, and to understand the energetics. How is the black hole interacting with its environment and feeding energy into the galaxy that it lives in? How do we understand how it changes in time, its variability, and what kind of extra information can we glean from looking both at the horizon, at the emission very close to the black hole, and the larger scale emission? And so all of this is done using a technique called very long baseline interferometry. Pierre promises me that many of the students in the room actually had a lecture about this in the context of ALMA, or at least long wavelength observations. So the Event Horizon Telescope is not a single telescope. It's not one dish that looks at the sky. It's actually a collection of observatories that are spread across the globe. So this is a picture of one of the arrays that was used to observe, in this case, M87. And then when we observed Sagittarius A star, a few of these different observatories were not online and a few others joined in. So these are truly a global array of telescopes. And we connect them together to almost sort of place little tiny mirrors just at particular spots around the globe. And at those moments, at those particular positions, we can image the black hole. And as the Earth turns, we get a slightly different collection of observatories watching the black hole. And we synthesize from this data, from this collection of data points that allow us to look at the black hole over a very long baseline, we call it, we're able to make a sort of synthetic image of the black holes. So how does this work? You have two different observatories. Here, we're just using two as an example. The distance between them, we call a baseline. We take the data and we look at these two wavefronts. So the two squiggly lines you're seeing in yellow, we measure their time of arrival. And we can understand exactly the precise emission from the source by correlating those two signals in a big supercomputer, which we call a correlator. And so this is the technique of interferometry. It relies heavily on a very large array of computers actually correlating all of these signals. We have to time these wavefronts very accurately at all these positions around the globe. And we also rely heavily on having beautiful, perfect weather everywhere on Earth, all at the same time. So obviously this is not the way it works out most of the time. And so we have to really struggle to get these observatories all online, taking data at the same moment. It's really quite a big effort, and in many ways, truly a very human endeavor also. So this is what these baselines look like. This is how you synthesize a VLBI image. So this is the data that were collected on Sagittarius A star, our own black hole, in 2017. And you can see this is a sort of a virtual plane, a Fourier space plane, where you see how much observation you have at a given resolution, how precisely you can image the data as the Earth turns around. And you can see the most important thing to take away from the plot on the right-hand side here is that it's mostly white space. That means that we have very imperfect, incomplete information about the black hole. We have only data points at these positions where you see the colored lines, and we have to infer or try to figure out what the missing information might look like. And this is an important source of error when we go through, an important source of uncertainty in our imaging and in our inferences from that imaging that I'll come back to in a few minutes. Okay, as I said, this is really an effort that requires a lot of people. This is an image of the Event Horizon Telescope collaboration meeting happening in Granada, Spain last year. It doesn't just require a global array of observatories. It also requires a really global effort from an international community who come together to try to make these observations and to collect data sometimes for 24 hours at a time, and to coordinate all of these efforts and then correlate them all and then try to interpret and understand those data. Okay, so that's the background. These are the two black holes. So I've already introduced you a little bit to Sagittarius A star and M87. So here on the left-hand side, you see M87 star. It also has a beautiful Hawaiian indigenous name, Poehi, which means the vast unknowingness of darkness, I think, or something like that. It's from the creation poem of the Hawaiian peoples. So one of the observatories that we use as a part of this array is on Mauna Kea, which is a sacred mountain in Hawaii. So this has been a really great collaborative effort with the Hawaiian people to try to help bring these discoveries into their sort of narratives as well. And Sagittarius A star in the Milky Way galaxy. So I want to point out, because I'm going to reference the size of these rings a few times as we talk about these two black holes. So remember, what we're seeing is hot material very, very close to the event horizon. Hopefully everybody in the room knows once material has fallen across the event horizon, we can't see it anymore. It's effectively trapped inside the black hole. This is true of atoms and electrons and molecules. It's also true of photons, of the light, of electromagnetic radiation, of magnetic fields, et cetera. So the dark hole, if you will, that you're seeing in the middle is stuff that is sort of a darkness that we can't see because there's no emission coming out of it. The material on the outside of the event horizon, still just outside of that point of last return, is very hot. It's fallen into a very deep potential well, and it's radiating, and that's what we're seeing. So in all of these cases, you're seeing the sort of material that has not yet fallen across the event horizon, and then you see some additional structures. Some of these structures are actually features that come from lensing, from bending of photons. So if you imagine this is a black hole, it has a lot of hot radiating material around it. It's rotating some of that material on the bottom, for example, of the M87 image is rotating in your direction. So it is beamed a little bit, it's boosted a bit by moving toward you, and then it's deboosted as it moves away from you. So you can imagine this as a sort of a lensed, rotating hot plasma very close to the black hole. The emission from Sagittarius A star is a little bit less well organized. I can't give you quite as descriptive a picture. Some of these blobs around Sagittarius A star might be connected to hot pieces of the accretion flow as it moves around, but we're not very confident in that yet, partly because of that missing information I was talking about before. Also, along certain lines of this image, we have a little bit more sensitivity in our observatories. So you get kind of an enhancement of emission that is artificial, if you will. It's just a place where your array was a bit more sensitive. So what we really look forward to doing, and I will come back to this again for Sagittarius A star, is watching this black hole change in time. If we see a structure like that bright blob you're seeing in the upper right rotate around the black hole, that will give us more confidence that we're seeing a real feature, an actual enhancement of emission, a blob of extra plasma that's orbiting around the black hole. As yet, we're not ready to make any claims about that from the data we have. So these rings, because these rings are guided by this sort of bending, this gravitational lensing of photons, their size can tell us something about the mass of the black hole. So in each of these two cases, I'm telling you the ring size in micro arc seconds. So remember, an arc second is a measure of the angle on the sky. In this case, we're thinking about how big something is on the sky. And this is micro arc seconds, so a very, very tiny fraction of a degree. So these are very small images in projection on the sky. So M87 star is 42 micro arc seconds. This corresponds to about 8 gravitational radii. Sagittarius A star is slightly larger, around 50 micro arc seconds, around 10 gravitational radii. So these are the two black holes that we've managed to image. They are not the same size. Okay, so remember back to that first slide that I showed you, and I said they're different by about 3 orders of magnitude in mass. These two black holes are actually extremely different in their physical size and in their mass. They look very similar in projection on the sky, but one is actually much, 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 much further away. So M87 star is a very massive black hole at a much larger distance. And so if you were to try to compare these on a more physical scale, if you could walk right up to the black hole, which I don't recommend you do, but if you could walk right up to the black hole, you could get a sense of how they differ in size. So here we have an XKCD comic way of thinking about these two black holes. So here's M87 star. In the little ring in the middle, you can see what would be Pluto's orbit. at that same distance, and the Voyager spacecraft, which is the spacecraft that humans have managed to fling the farthest away from us out into space. So the Voyager spacecraft is just now outside of what we call the heliopause. So it's just outside of the sun's influence now. This is the most distant thing humans have ever managed to eject out into space. So you can see that something slightly larger than Pluto's orbit is the sort of rough size scale for the event horizon of M87. And Sagittarius A star, if you were to take the Sagittarius A star black hole and put it into the M87 system, it would be way inside of Pluto's orbit. So you see Mercury's orbit, sorry. So remember Pluto, a very distant planet out at the very outer edges of our solar system. Mercury, the innermost orbit, the innermost planet orbiting our sun, is sort of more like the scale of Sagittarius A star. So these two black holes, even though they look like they have the same size in projection on the sky, or very similar sizes, are actually quite different in size. And this has to do with the black hole masses. So M87 star is 6 times 10 to the 9, so roughly 6.5 billion times the mass of our sun. Sagittarius A star is 4.2 million times the mass of our sun, hence the 3 orders of magnitude difference roughly in their masses. And those differences in mass lead to their very different physical scales. So the other thing that is very different between these two black holes, and again, intimately connected to their mass, is the time scales on which they vary. So believe it or not, the M87 one on the left-hand side here is changing. If you look at it long enough, you'll see it's evolving in time. The one that you're seeing on the right is Sagittarius A star. It's changing on a much more kind of rapid timescale. These are Sgr MHD, general relativistic magnetohydrodynamic simulations. These are not real images. These are simulated images of what we think these two black holes look like as they vary. I'll just replay this so you all can watch that while I talk. M87, because of its mass, varies on timescales of something like months to years, and maybe sometimes on shorter timescales like days. Sagittarius A star varies on minutes to hours. Remember, I told you at the very beginning, the way we make these images is by using baselines between telescopes all around the world, and as the Earth turns, we take an image. Sagittarius A star is a big challenge to that kind of imaging because it changes at the same time that you're trying to image it. And that makes creating an image really hard. So this is a really interesting property of the two black holes. Sagittarius A star is considerably more difficult to work with because of this very rapid timescale. It also makes it very interesting, but it's a challenge. Okay, so this is the more sort of detailed way of comparing these two black holes. Sorry, I switched them. I should have kept them in the same order, but now we're looking at Sag A star on the left, M87 on the right. You can see the masses that I just mentioned. You can see that the accretion rate, the amount of material that's falling onto the black holes, is very small. So to a person in the audience who is, interested in accreting supermassive black holes, neither of these would be classified as an AGN or a quasar. They're low luminosity systems. They have very small amounts of mass falling onto them. So 10 to the minus 7-ish and 10 to the minus 3-ish solar masses per year. Again, you can see they differ quite a bit from each other in how much mass they're accreting annually. Their luminosities are quite different. Their Eddington ratios are quite different. And we think that the material feeding these black holes is actually quite a different origin. So for M87, we think there's sort of a smooth accretion flow, a little bit of mass falling in. For Sagittarius A star here in our galaxy, there's no reservoir of gas, which is why its mass accretion rate is so low. In fact, we think that the mass that is falling onto Sagittarius A star comes from the stars orbiting around. I told you before, one of the ways we measure its mass is by these massive stars that are in orbit around the black hole. Those massive stars have winds. They blow material off their surfaces. And that wind is just very diaphanous, very, very low density plasma. And that little bit of wind from the stars is the material that's available to fall down onto the black hole. So I mentioned this before, but these really are ecosystems. They're whole environments that are interacting at a lot of different size scales. And so that makes them very interesting to study at all of these different size scales and wavelengths to understand what's going on. M87, as I'll show you in a minute, you haven't seen it really yet from these images, has a spectacular jet, a huge jet that just flies out of the galaxy across 7 orders of magnitude in size. Sagittarius A star, based on our models, we're sure it has a jet, and we can't find it. So we might just be wrong. All of our models predict a jet for Sag A star. We've never been able to conclusively locate in observations a convincing jet from Sag A star. So we think it should be there. It's possible it's tipped right along our line of sight, and that makes it really hard for us to see. And there's some hints from our observations that maybe an inclination angle that makes it sort of disadvantageously pointed torus makes this an extra challenge. As I've already mentioned, the time scale for variability for Sag A star is much shorter than for M87, and you'll see that in the data I'm going to show in a minute. Oh, here we go. We can actually see how this scales with mass. So this is a very nice plot from Jeff Bauer and collaborators. You can see the characteristic time scale for variability is the vertical axis, like what is the kind of average timescale for variability for a black hole, plotted against black hole mass along the bottom. And you can see the 2 black holes we're talking about circled in color here, Sag A star and M87. The arrows are limits, so we don't actually have good measurements for very many supermassive black holes. M81 is the black hole in the center of the Andromeda galaxy. Based on its distance and its mass, its horizon is too small for us to image with the Event Horizon Telescope. I'll show you that one more time at the end of the talk, but that's a source for which we cannot observe this donut of light because it's just too small. We just see it as a point. We can't see that horizon for M81. So the two sources that the Event Horizon Telescope in its current configuration can observe the horizon are Sag A star and M87, and you can see this almost linear relationship between, well, it's a log relationship between the black hole mass and the timescale for variability. Okay, so here is a really cool zoom in, mostly at radio wavelengths, of what the environment looks like when we drive our observations in through the center of the Milky Way galaxy and all the way down to the event horizon. So you can see that the environment is very rich. It's very complicated. There's a lot of magnetic structure. We just passed by what are called the mini spirals. We think they are sort of interesting spirals of material. And then we zoom all the way in at very, very, very small scales and find the black hole in the middle. This is observations all taken at radio wavelengths. So you couldn't see those stars that I was talking about because they don't emit at radio wavelengths. But I'll show you a picture of what they might look like in a minute. First, I want to talk a bit about how we created this synthetic image. So I emphasized how much white space was on that coverage plot when I showed you the interferometers observing Sagittarius A star over the course of a night. So we have to basically go in and say, well, we're missing a lot of information. What about if we make this assumption about the missing data? We can reconstruct one image. What about if I make a different assumption about the missing data? I can make this image. And we do these reconstructions again and again and again and again. So we basically go through our whole parameter space. We study all of the synthesized images that we can make. And then we classify these synthesized images that fill in that missing information in a bunch of different ways. And when we do that classification, we come up with kind of 4 big categories of what this image might look like. And you can see those 4 categories at the bottom. And then we weight them by how often that category of image comes up, and we basically co-add them, weighted by how often that kind of image appears in our synthetic catalog. So these are the 4 subset images that have been averaged together in a weighted average to make that image at the top, which is the image that you've all seen of Sag A star. And you can see these 4 images have things in common. They each have hotspots, but they don't always have exactly the same number or same position of those hotspots. You can see the last one doesn't even really quite recover the horizon. It doesn't quite have that dark shadow in the middle. But you can also see that that last one that doesn't favor the shadow is the least common of the synthesized images, right? If you look at these little histograms, you can see the first 2, the blue bar and the pink bar. Those are the 2 most common ones. And then these last 2 are ones that are sort of disfavored by our synthetic imaging. So when you hear people talk about how we made an image of this first image of the supermassive black hole, these are images that are deeply tied to the data, but it is not a perfect reconstruction because we have a lot of missing information in our observations. Okay, so this is how this classification works. We basically use supercomputers to fill in all of the information that we're missing, and we create huge catalogs of synthesized images. So in this catalog, I believe we ended up with something close to 10,000 synthetic images. We use machine learning classification to sort them into different categories. And then because we're all suckers for punishment, we also use human classification. So those human beings you saw on that first slide, we went through all 10,000 images and classified them also. And it turns out the machine learning and the humans basically agree that there are sort of roughly 4 categories of images. When we do this sorting, they fall into sort of these different classes that I showed you already as the 4 kind of parent images that are most common. And so the combination of a very fast algorithm and a whole bunch of willing graduate students and postdocs and faculty allowed us to make this classification and sort of figure out how to do the weighting to create the black hole image. Okay, so that's a little bit what goes into the sausage. And then just to zoom out a little bit, I want to put this image and this black hole into its broader context. For this is the work that I've been very intimately connected to. We also get every other observatory we can get our hands on to watch the black holes at the same time that the Event Horizon Telescope is making this horizon scale image. Why would you do that? Well, you want to understand the environment. You want to understand the variability of the black holes. And you also want to be able to connect these observations up to decades of observations we've been making of these black holes as astrophysicists all the way up until the present day when we can actually do the horizon scale imaging. So you want to be able to connect that context up so that you can use all of that legacy data to understand what's happening to the black hole, how the accretion is evolving, whether or not you're seeing phenomena at the horizon. Okay, so this is my one picture of the sort of bigger context. I've showed you already a little bit about the image that you're seeing down on very small size scales. I've given you a lot of different ways of thinking about the size of this. So remember, I showed you that picture that sort of points out that the black hole sits in something that's like inside of Mercury's orbit. For those of you that think in astronomical units, so an astronomical unit is roughly the average distance between the Earth and the Sun. Sagittarius A star, the size scale for this black hole is something like half of that Earth Sun distance. That's an astronomical unit, half an AU. If you zoom out a little bit, so I'm marching across this bottom panel. If you zoom out a little bit, you're seeing an artist's impression of these stars I keep talking about. These stars orbiting around the black hole, and their stellar winds are what create this hot gas that can then fall into the black hole. If you zoom out even more, in addition to this kind of spherical structure, we see some flattened orbiting structures. And that out at even larger scales, you see all those amazing gas structures that we saw for that little zoom in video. Up on the top, you're seeing now data from an X-ray observatory called the Chandra X-ray Observatory. And you can see that hot gas. So Chandra as an X-ray observatory sees temperatures that are sort of 10 to the 5, 10 to the 7 Kelvin. So this is extraordinarily hot plasma, very, very hot gas. And you can see that hot gas sort of distributed around the black hole. The last image in the upper left here is a zoom out of that hot gas. And the blue circle is showing you sort of the gravitational sphere of influence. We call it the Bondi radius. It's sort of the region within the black hole's ability to accrete that mass. The thing I want to point out to everyone is that this hot gas that we're seeing in the images from the Chandra X-ray Observatory, the artist that worked with us to make this image is trying to depict that as that kind of fuzz in the bottom, the image just below it at 0.15 parsecs. So the important thing here is that these systems are they're not disconnected from one another. These stars are orbiting around and punching through this hot gas. They basically make this hot gas reservoir. And so this is a complex environment where these different components are actually interacting. And when we do observations, sometimes we only see one component of this interaction. And so it's easy to forget that they're connected to one another. So the multi-wavelength is really helpful for helping us look at how they match up. So this has allowed us, these kind of multi-wavelength observations have allowed us to understand the conditions of this hot material falling into the black hole over many different radial radii. So that Bondi radius, that blue circle, we have marked here as a purple line at something like 10 to the 5 Schwarzschild radii. And the total sphere of influence is out a little bit further. And as you march in, you can use a whole bunch of different measures to try to understand what's happening to the accretion flow, understand the density, understand the temperature, the sort of equation of state, if you want, for the gas. And so we use this, at the largest radii, we use those stellar winds, measurements of stellar winds. Then we can use the X-ray luminosity, which I was showing you in the image. We can see what the profile of that luminosity looks like. Then we can actually look at drag forces on objects orbiting around the black hole. We can look at radio measurements of the so-called rotation measure. And then we start to be able to get in really close to the black hole with submillimeter and radio observations, when we can really start to look at the size of the black hole shadow. And potentially the purple bar you're seeing at the top there, you can learn stuff about the flares that we see kind of daily, roughly, in the X-ray. So I'm going to talk for a minute more here about flares. And I want to just sort of emphasize these interesting flares we see from Sag A star. So I talked a lot about how the variability timescales for the black hole are very short. And one of the ways that we've known that for decades now is by looking at these interesting flaring events. So for Sag A star, when you look at it at X-ray wavelengths, we see a bright flare something like once per day. And we've never really known whether or not these flares are a horizon scale phenomena. Is this something that's coming from right next to the event horizon? Or are we looking at something maybe like an eddy, some other little sub phenomena further out in the accretion flow? At X-ray wavelengths, we can't see right down to the horizon. We can only do that right now with submillimeter measurements. And so we've had to make a lot of inferences based on the data that we can get and the time scales and all sorts of assumptions. But if we can observe an X-ray flare at the same time that we observe the event horizon, and we see some sort of variation in the event horizon emission from the Event Horizon Telescope, now we can actually say more definitively that these flaring phenomena are truly due to some sort of orbiting material or interesting phenomena right next to the black hole. And so people have been debating for decades now whether or not the flares are being driven by an orbiting plasmoid, or whether we're looking at interesting magnetic reconnection. If you take magnetic fields and you twist them up as the black hole spins, they get too close together and they kind of effectively break and they accelerate a whole bunch of particles. That's called magnetic reconnection. You might actually have an asteroid that gets a little too close to the black hole and gets shredded, tidally shredded apart. And it's also possible that more than one of these things is operating at the same time. So we can use these really amazing observations from EHT and multi-wavelength to try to model the spectral energy distribution, the distribution of energies as a function of time, and try to understand which one of these is the most compelling explanation for these flares. We can also try to get at some of the plasma physics, the microphysics. What's the emission mechanism? What's the radiation? Do we see synchrotron radiation? Is it some combination of synchrotron and Compton, et cetera? And we can try to map that out as a function of distance from the black hole. So this becomes a very, very rich physics problem as you are able to see all these different interconnections at different wavelengths over time. So the time component plus the wavelength component is very helpful for these studies. Okay, so this is the EHT campaign seen not through the images, but through so-called light curves. So you're looking at flux, sort of, in this case, X-ray or radio brightness as a function of time. These are 3 days where we observed with the Event Horizon Telescope in 2017. The first 2 days, if you look at the top green lines, those are from ALMA and SMA. So these are sub-millimeter light curves of Sagittarius A star on those 2 days, and it's fairly constant. Remember, I told you we want to make a synthetic image, and those synthetic images require source stability while the Earth rotates. So we were really happy that it didn't do very much for a couple of days. It was just sort of a quiet black hole for once. And so when we show you images of Sagittarius A star, I spent all this time explaining to you how we built those images. We're only using data from these first 2 days, from the 6th and the 7th. And the reason is that those are 2 days where the black hole was relatively stable, and we could actually build a synthetic image. You'll see on the last day, the black hole was not as stable. There's an X-ray flare, which you're seeing in the blue. That's from the Chandra X-ray Observatory. In purple, you're seeing New Star, which is another X-ray observatory observing at slightly higher wavelengths. And of course, because nature is not always kind, we actually don't have EHT observations right at the time of this flare. They pick up just at the end of the flare. But you can see that there's a big peak in the submillimeter light curves as well, just after this bright X-ray flare. So we did not include these data in the imaging that we did because that would have complicated the analysis. So we just left it out, but we can look at how the light curves tell us about how the black hole is responding. So on April 11th, we're still hot, kind of on the hunt for a good explanation there, but I'm going to show you some preliminary results about what we think might be going on. So this flare on April 11th, when you look at it in the kind of bigger context of a bunch of flares we've observed from Sgr A, we're looking here at fluence, which is just sort of the total amount of flux in a flare versus how long the flare lasts. The arrow is pointing out this particular flare. So it's a pretty run-of-the-mill flare. It's average. It's not so bright. It's not so faint. It's kind of a normal flare from Sgr A. So in context, this doesn't look like it's a particularly exotic flaring event. But it's very interesting because of this rise in the ALMA and SMA light curves just afterward. I'm going to skip over this. Oh, maybe I'll just say very, very briefly that we can do some nice spectral analysis. So we can look in detail at the energetics of these flares. And if you do that and you make a few simplifying assumptions about how much volume could contain the energy in the flare, you find something that is about 10 gravitational radii. For the very clever among you, you might remember that I told you that the event horizon for Sgr A, that 50 micro arcseconds, was something very close to 10 gravitational radii. So it actually looks like if you just do simplified arguments here, the flaring phenomena are consistent with coming from a position that's very close to the event horizon, at least in terms of sort of a generic size scale. So this is the kind of game we've been playing for a long time. Yeah.
X-ray flares.
Yeah, in some models, the question is whether or not you would see a delay in the sub-millimeter compared to the X-ray flares. And in some models, yes, and in some models, no. If you think of this as just an sort of adiabatically expanding blob of plasma, and you do the energy injection from, say, magnetic reconnection, so you have magnetic fields that reconnect, they accelerate a whole bunch of particles. That acceleration is going to appear first at high energies, and then as it expands and cools, you'll see a responsive emission at sub-millimeter wavelengths. So in that scenario, yes, you would expect to see a delay. But of course, the tidal disruption of an asteroid is a slightly different scenario. So hopefully, if we can actually definitively pin these wavelengths together, we can actually start to choose a model or prefer a model over another. But the fact that we have this pernicious gap right at the moment of the X-ray flare is we run into this all the time. It's very hard to get long time scales of observations where everything overlaps and the black hole is kind enough to give you a beautiful flare while you're watching. So it makes the analysis just a little more tentative. Okay, so we have done some nice work. This is work led by a collaborator outside of the EHT, but he's among our collaboration members. I'm not going to spend too much. This is a little bit of a complicated plot, but what you're seeing in the top left here is that same gray bar showing you where the X-ray flares happened, and then the ALMA and SMA light curves in color there. And what they did here is they actually looked at polarizations, the orientation of the magnetic field based on measurements from the radio and submillimeter data. And they actually find that this is very consistent with having a polarized, so sort of a magnetically organized hotspot orbiting around the event horizon, the black hole, very close to the event horizon. So for the experts among you, you're looking at the QU plane here, and you can actually see the sense of orbit here in the black hole. I don't have a laser pointer that's working, but if you look at the little inset, it even does a funny little subloop. I don't know why it stopped working, Marta. We tried, but maybe you have the magic touch. There's a little subloop, which is actually indicative of a little bit of a lensing effect as the black hole kind of goes around the back. The hotspot goes around the back of the black hole. So this is looking very exciting. Did you figure it out? How are you so smart? Okay, So here we go. This is the third time Mars has been amazing since I've been here. Okay, so it orbits around this way, and then you see it does this little funny extra loop and then comes around. And this is based on the polarization measurements, and this is exactly consistent with what we would expect if we had some hot blob of gas that is orbiting around the supermassive black hole and at the same time expanding as it orbits. So we're starting to get excited about maybe, achieving this goal of seeing plasmoids, of seeing hotspots in the vicinity of the black hole. This is linear polarization. We haven't done circular polarization yet. So this is, hopefully we're going to do a more detailed polarization study coming up in the next 6 months or so. We've just started, I'll show you very briefly some of the polarization studies for M87. We've done linear polarization for M87 also. It's a very different system. We don't see these timescales. And the circular polarization paper was just submitted. So that's also coming up, but it's a little bit more tricky. And so we're just marching our way toward achieving that. Yeah, thanks for the question. And we hope that this is going to, teach us more as we get deeper into the data sets. Okay, last thing I'll say about Sgr A, and then I'll hurry up and get through M87 and wrap up pretty soon here. So this is a much now broader range of energies. I showed you those light curves before. This is now, instead of showing you brightness versus time, I'm showing you frequency, or nu L nu, so the luminosity weighted by frequency versus frequency. So this is sort of like energy along the bottom axis and luminosity or brightness along the vertical axis. And so this is now the broadband SED of Sgr A. So this goes all the way from radio wavelengths all the way out to X-ray wavelengths. And you can see that the black hole is brightest here in the millimeter. This is where the EHT observes Sgr A. It's not an accident that EHT looks at the black hole in the region of wavelengths where it is the brightest. This is where you have the best opportunity of making an image. It also can tell you something about the energetics of that plasma. You will see it rises and then falls, and then it has this extra high energy component. And sometimes this is what the X-ray energies look like when it's not flaring. And this is what the energies look like during that April 11th flare. So you can see there's a lot of variability. These yellow bars in a few places are showing you the kind of range of variability that we've observed at those wavelengths. So you can see that the black hole is much more variable at certain wavelengths than others. And in some cases, like the flares, it's very distinctive in time. So we can use these multi-wavelength data to help us understand the simulations that we make based on GR and magnetohydrodynamics. We can use them to add some additional constraints. So this is where I'll finish talking about Sgr A. When we put all these constraints together, we find that the multi-wavelength plus EHT imaging results favor a very low inclination. Remember, I told you we think that it's kind of pointed toward us, this black hole's sense of rotation. We also favor cool electrons compared to the ions in the flow, very turbulent plasma, and very strongly magnetized accretion flows. So this is helping guide us toward which kinds of models are most likely to be consistent with the observations. And in particular, one thing people always want to know about is spin. So this is a kind of a difficult visualization, but everybody always wants to know, is the black hole spinning fast? Is it spinning slow? This can tell us something about mergers and accretion and the physics of formation of black holes. So these are various different spin parameters. So this is a non-spinning system. This one is spinning prograde. These ones over here, these are spinning retrograde. And the quadrants, so the bottom quarters are showing you magnetically arrested disks, they're called, very strongly magnetized models. And the top ones are showing you a different accretion model. And then the different quadrants are showing you different inclinations. So how tipped the system is toward your line of sight. So the important thing is that everything red means it does not match the observations. So we can rule out many, many, many different model parameters. And we can prefer certain areas of the sort of parameter space here, which is how we come up with numbers like roughly 30 degrees for the inclination and a relatively high spinning black hole rather than one that is not spinning at all. So this is not a firm constraint on the spin, but it is sort of illustrative of how we might be able to do better at constraining a black hole's spin as we go forward. And in particular, let's see if I can find it here. The stuff that is hatched, if I'm not mistaken, is a constraint that came from multi-wavelength observations, not just from the black hole. Okay, then my last movie. So how do we do this? So I told you before that we have this huge database of synthetic images, and then we select out the best synthetic images to try to make a nice black hole representation. This is now how we use another library. This is a model library now of GR MHD simulations. So these are simulations run on a computer of our best guess at the accretion models that describe these black holes. And we can then compare these GR MHD simulations to the real data. And the data can help us rule out model instances and help us kind of decide on which models are the best. So I'll play this video one more time, if I can. And you'll see here, these are GR MHD simulations that vary in time, which is why you're seeing them change. They have all sorts of different properties for luminosities and different wavelengths and energetics. And we can use the different properties. The size of the EHT image rules out a whole bunch of things. The shape of the EHT image, how circular or non-circular it is, rules out a whole bunch of other things. The multi-wavelength spectrum rules out a bunch of other models. And then the size, when we compare it to other frequencies, does an even better job of ruling out models. And so this is the way we use the combination of simulations and observations to try to narrow down the modeling that is the best for helping us understand Sagittarius A star. And I will say that even though you see here on the screen 2 models left, it turns out that in the study that we most recently did on Sag A star, that none of the models work very well. And the thing that is a problem is that all of the models have too much variability. They have too much time domain, too many changes in time on short time scales to match the data. So even though this black hole is very variable, our models are still too variable compared to the observations. And so this gives us an opportunity to try to revise our models and do a better job of describing the black hole. Okay, quickly, I'll just show you some of the cool things about M87. So once again, much like Sagittarius A star, we have an amazing black hole image here. As I was saying when we talked a little bit about polarization, you're now seeing polarization vectors sort of superposed on the black hole image. And we also had a beautiful multi-wavelength campaign to study this source. And you're going to see how different this source is when you look at these multi-wavelength data. So this is that black hole image down here. And as you march out, we're marching out in size scale, you can see that there's actually a spectacular jet being driven from very close to the position of the black hole. So we're going out to larger and larger scales. This is 0.013 light years. This is 1,300 light years. And then when we look at X-ray and optical, so this is optical and this is X-ray, M87 has this enormous jet that is just flying away from the black hole and interacting with the galaxy over huge distances. And we see it all the way out to very, very, very high energies with the Fermi-Lat Observatory and the Hess and Magic and Veritas Cherenkov arrays. So this is a jet that is observed at many, many different scales and at many, many different wavelengths. And it is a very different beast than Sagittarius A star. This is an X-ray image of some of the really interesting magnetic structures that seem to be maybe perpendicular to this beautiful jet. And then here you can see the polarization vectors for the horizon scale, and then also in the very kind of lumpy base of this jet. So this gives us an opportunity to try to understand how jets and black hole horizons, accretion flows, are connected to one another. We've thought, this is sort of an artist's impression from our colleague Sarah Markoff. Here's the picture we, tell ourselves. You start with a black hole. The black hole has accretion around it. There's some sort of thing happening in here called a corona, which nobody really understands. We just wave our hands. We say it's magnetic, it's hot, there's something going on. And from down here, we launch these jets. And we see these jets in many, many different black hole systems. And we'd love to do a better job of constraining the various different ideas about how these two pieces of the system are connected with observations. And we do this often by looking across many scales and different wavelengths. And we often use for very, very bright systems something called a one-zone model, where we assume when we look at, this is another SED, this is flux versus frequency, so energy versus sort of overall brightness. We use a one-zone model where we say we think a lot of the emission is coming from this one bright knot in the jet, for example. And then we use that model to try to understand all of the different data that we collect. So we've tried to do this for M87. So this is, again, much like the one I showed you for Sag A star. You're looking at overall brightness versus energy. And you can see again, much like Sagittarius A star, we think that this SED peaks and kind of millimeter wavelengths, and then it has a very high energy component here out at the TeV energies. And so we've worked very hard to try to understand how to model this jet using these sort of simplified one zone models where we just assume all the emission is coming from one bright spot in the jet, motivated by studies of other black holes out in the universe. But it turns out that if we try to model what's going on at low wavelengths, our models fall way short of the high energy emission. If, on the other hand, we try to say, well, let's just imagine we've got some sort of boosting factor in there, something that takes the low energy emission and sort of bumps it up, reprocesses it up to the higher energies. We can do that, but it requires sort of a huge amount of extra interaction between the particles, so much so that it's not really quite a physical model. And so we've tried moving our zone around to see if we can do a better job of fitting this SED. So when we put this green zone very, very close to the event horizon, you can see that we get models that seem like they can do an okay job. These are two different possible models of the low energy, and maybe these are the X-ray data here, but they really don't do anything for the highest energies. So, okay, maybe that's not a perfect model. What about if we move the jet, the zone somewhere else? So let's move this jet, this knot that we're modeling a little bit further out in the accretion flow. We can get a little bit better fit to the higher energy emission, but now we're falling way short of the low energy emission. And so what this has demonstrated to us very clearly, kind of skipping over a lot of the more nitty-gritty plasma physics here, is that a single zone is not a sufficient model to help us understand what's happening with M87. We really need more complex models that model multiple zones and maybe even manage to tie the processes together between the different zones in the model. And so this is great, right? We all love this, theorists love this, we're going after this data. And the other thing that's great about all of these observations is that we have multiple years of observations. So as I mentioned before, we were very lucky that Sagittarius A star was observed when it was quiet. Similar thing for M87, our first observations in 2017, the black hole was very quiet. So this is, you know, the black hole kind of bumping up and down over many years timescales, but in 2017, it just was like a sleeping giant. It was very quiet, which gave us a fantastic opportunity to take a picture of it without it varying around and doing all sorts of weird things. And so that's great. That was really an opportunity for us. I will foreshadow that in 2018, which is the second year of observations, it was not a sleeping giant. And so this is coming out soon. We're just finishing up the paper writing about the 2018 data and looking over multiple years, as I pointed out, for M87 makes more sense because its variability timescales are kind of months to years instead of hours to days. And so this is exciting, and you'll see more about it again soon. As I mentioned, we've also done some sort of early polarization studies on the emission from M87. These are the polarization, the total intensity, polarization fraction, and electron vector position angles are these little things you're seeing in color up at the top here on the 5th, 6th, 10th, and 11th. So you can see sort of what the polarization looks like as a function of time. And we're working more on the polarization studies. I think these are going to be really, really, really rich for helping us understand what's happening with this disk jet connection going forward. And circular polarization, as I mentioned, is coming up too. This is the last sort of sciencey thing, and then I'm going to go through some quick just wrap up. I know we're getting... we're already late. Okay. So a very cool paper just came out maybe a month ago, trying to actually do the connection between the horizon and the jet. So you can see here, this is looking at slightly longer wavelengths. When you look at longer wavelengths, you can see that the emission, the horizon, the ring, if you will, is a little bit larger. And we also see this really interesting connection to the base of the jet, including maybe a jet spine, which is very interesting to the modelers. And when we compare this to what we would expect, we actually see that the jet is a little bit broader. It's wider here than we expect based on what we see out at larger radii. And this is indicative, we think, of there actually being not only the collimated jet, but also a wind being driven off the accretion disk at the base of the jet, causing the base of this emission to look a little bit wider than it would otherwise. Okay, There's lots more data coming, as I've mentioned a few times. We have only so far shared data from 2017. We have observations in 2018, 2021, 2022, and 2023. These include coordination with James Webb for the first time. So this is very exciting. We're hoping to catch some flares and maybe be able to look at infrared flares in connection with the EHT as well. We have other AGN that we're studying. This is a beautiful JET paper on Sgr A that was published just recently. And we're also thinking about future upgrades. So these are just the flash through a few things that we think are really cool. So observing with James Webb is going to be very fun. It's a very hard observation to make because there's a lot of confusion in the Galactic Center for James Webb, but we're hoping this is going to be a rich area. We'd also love to go after other black holes. So these are the two black holes I've spent this whole time talking about, but there's a lot of other black holes out there. So it would be very nice if we can push our instruments to be able to go after some of these black holes. Even if we can't get their horizons, studying their jets would be very cool. We hope maybe with future versions of this array to maybe be able to go after lower mass black holes, so stellar mass black holes that have accretion disks and jets, much like the ones that you've seen from M87. So this is very interesting, but requires much better time resolution from the observatory than we currently have. So an exciting direction, but one that is still not quite achievable with the array as it looks right now. And of course, it would be amazing to be able to look at binary black holes, should we be able to find one that is a convincing local enough candidate, but this could be done in synergy with PTA, the pulsar timing arrays, and maybe LISA in the future. And so once again, this is just showing you the sort of array of black holes here now. This is ring diameter, I should have said that before, versus how bright they look to the EHT. We think that there's a lot of interesting science that could be done if we could actually go after some, resolved systems if they were close enough for us to look at. This is just the same plot here, but showing you in a different depiction. So all of this stuff is exciting. It's written up in a compendium of papers that were just published in the Galaxies Journal just in April of this year. So if you're interested in kind of future Event Horizon Telescope stuff, there's a whole bunch of papers that you can go and read there. So I will just skip over my summary slides because I think I've said everything multiple times, but we can come back to them if you want, and I will stop there. Sorry for running a little long.
Thank you very much. I love it. Questions?
Very nice talk. Thank you very much. In stellar mass black holes, we has been seen that before the ejection of jets, the X-rays, the X-ray state changes from hard to soft. And this is a very rapid change. And the interpretation is that the inner part of the accretion disk is blown away. Is blown away and because of magnetohydrodynamics is pointed along a jet. Do you have in this flare in Sagittarius A star observations in the X-rays that could indicate an analogous behavior? I mean, it would have been nice to see integral observations at the same time. That would have been great. Well, this is a question. And then the second question is what are the prospects to increase the frequency of the Event Horizon Telescope?
Great. Those are both great questions. Let me take the second one first because it's faster. So yes, we are already observing at higher frequencies. So currently the EHT images I've showed you are all at 230 gigahertz. We've already started observing at 345. So in the campaign this year, we had 345 observations, 345 gigahertz observations of Sag A star. As you probably know, the higher frequency has more dust and kind of a lot more confusion. We have to do a much better job of getting rid of all of the scintillation and problems along the line of sight. So it's a harder observation to make cleanly, but it's very exciting because then you could actually get some sort of spectral information from the black hole imaging. So yes, we're pushing very hard. And then the next generation EHT would have even potentially a third possible window. So lots of effort going into trying to do higher frequency observations. The first question about the hysteresis diagram, the state changes for black holes, for lower mass black holes. We don't have those beautiful, smooth outburst sort of diagrams that you see for stellar mass black holes, but we have a few pieces of evidence that indicate that it might be similar. One is that during the flares, the X-ray spectrum of Sgr A becomes harder. So it does look like the photons shift to higher energy in the flare compared to in quiescence. So that's sort of analogous. It's only during the flare we have a fairly crude estimate of how that's happening. The other thing I'll say about that is if you look at the black hole fundamental plane, where you're looking at black hole mass versus sort of a combination of radio and X-ray luminosity, Sagittarius A star does not actually sit on the black hole fundamental plane, except for when it's flaring. So during flares, it comes up and it sits on that fundamental plane. And that might be because it's sort of during those flaring events, it's more equivalent to an actively accreting black hole. The energetics are more similar to a more spicy system. And the rest of the time, it's just so quiescent. It's not even analogous to any of the black holes that you're seeing in the rest of that plane. So I would say it sort of is illustrative that it looks like the stellar mass black holes, but it's not, we don't have the same fully populated hysteresis diagram.
Thank you for this very beautiful talk. I have tons of questions, but I will not ask them all. Back to the simulations with the different models. Just by including the shape, you already rolled out plenty of these models. Why is that? Why is exactly the shape that affects?
Yeah, so a lot of the models, if you had sort of preferential accretion or sort of more variation in the accretion flow, you might expect elongation. So like if you look at the X-ray emission, for example, you'll notice the X-ray emission is quite elongated along one preferential axis. And so you can rule out certain geometries of the accretion flow by the fact that it's just so perfectly circular. The other thing that we'd love to do, but we can't quite do yet, and though Avery Broderick has a paper kind of hinting that we're getting close to this, is to actually look at photon orbits. So not just the plasma, the mass orbiting, but the photons orbiting. And the photon orbits should give you an even tighter ring around the black hole. And so this is something that we think is kind of convolved right now with all of the other hot plasma orbit information. But that would be an even tighter constraint on the GR models. And it's very geometric. You expect that to be a perfect circle if you're looking at the, a GR that conforms with, a black hole that conforms with GR.
Okay, so one last question from Luke, because this afternoon Daryl has a train to catch.
Thank you. In the case of Sagittarius A star, using the model for the hot spots moving on a very close by orbit, you show estimation of the spin of the black hole, but is it possible to exclude a spin larger than 1? In which case it will not be a black hole.
Yes, that's a good question. I actually don't do that model. I don't even know whether or not we tried to do spins larger than 1. My guess is that that's not even considered in these models. Though if you look at, so the paper's always done in numbered series, 1 through 6. Paper 6 of the Sgr A star series is a very deep dive on the theory and what's allowed and disallowed on the theory, including thinking about wormholes and deviations from GR. And so if you were looking for a resource to explore that, I would go look there. But my hunch is that looking for black holes that were, sort of super spinning or moving faster than, the spin parameter of 1, I don't think they were explored. But it's worth a peek there. I could be wrong. And there's really quite a bit of exploratory thinking in that last paper in the series, if you're curious about it. So I would refer you there. Sorry, I don't know specifically. I do know from another colleague that I think there's a lot of I think we should all be very skeptical of these spin measurements. I think we're probably overestimating the spins of most black holes based on some of the way that we model the accretion flows. So who knows, but I think there's a lot of, if we can get some better data to feed to people that think about simulations, I think this is going to be really interesting and juicy, and the polarization might be one of the great constraints.
Let's thank Daryl again.